Hey everyone, Bob here. Today, I would like to present to you the design and the function of a starting motor. The starting motor electromagnetic principles. Starting motors are designed to have a very low resistance and draw a very high current flow, which produces a high torque for short time periods. The field coils in a starting motor are made of heavy copper wire and are wound on steel pole shoes that are bolted to the starter case. One end of the field winding is connected to the positive battery terminal, and the other end of this winding is connected to an insulated brush in the starter motor. A copper commutator bar is soldered to its end of the armature winding. This winding is positioned between the pole shoes. The commutator bars are insulated from each other, and the insulated brush contacts one commutator bar. A ground brush completes the circuit from the other commutator bar to ground. Current in the starting circuit flows from the positive battery terminal through the field coils and armature winding and returns through the ground brush to the negative battery terminal. Because the field coils are connected in series with each other and with the armature winding, the same amount of current must flow through the field coils and the armature winding. A high current flows through the field coils and armature winding because these heavy windings have very low resistance. The high current flow through the armature winding creates strong magnetic fields around the sides of this winding. Since the current flows in opposite directions in the two sides of the armature winding, the magnetic field surrounding the sides of the winding flow in opposite directions. The high current flow through the field coils create a strong magnetic field between the pole shoes and the armature winding is positioned in this magnetic field. This magnetic field around the upper side of the armature winding is moving in a counterclockwise direction. An armature has many windings mounted in a laminated metal core that is pressed onto the shaft. Each winding is insulated from the other windings and from the mounting slots in the metal core. The ends of the windings are soldered to the commutator bars that are insulated from each other and from the armature shaft. Some armature windings are always in the magnetic field between the pole shoes to provide continuous armature rotation. Some vehicle starting motors have four field coils connected in series. All four of these windings contain heavy copper wire with very low resistance. Other starting motors have three series field coils and one parallel or shunt field coil. The shunt field coil has many turns of fine wire. While cranking the engine, the shunt coil has the same magnetic strength as the series field coils. The shunt coil creates a strong magnetic field from a low current flow through many turns of wire, whereas the series field coils develop their strong magnetic fields from a high current flow through a few turns of wire. When the engine starts, the starter turns freely for a few seconds until the starter drive is pulled out of mesh. This is called an overrunning starter condition. Under this condition, the armature could rotate at a very high speed. When the starter overruns, the battery voltage increases because the high starter current load is removed from the battery. When this action occurs, the current flow through the shunt coil increases and strengthens the magnetic strength around this coil. The strong magnetic field of the shunt coil creates an induced opposing voltage in the armature windings that opposes the battery voltage and reduces the current flow through the series field coils and armature. This action reduces starter armature speed and produces the armature. If the armature rotates at excessive speed, the heavy armature windings may be thrown from their armature slots, resulting in severe armature damage. Some starting motors have permanent magnets in place of wound field coils. In this type of starting motor, electrical defects in the wound field coils are eliminated. A permanent magnet starting motor is also more compact compared to other starting motors. The permanent magnets are manufactured from an alloy of boron, neodymium, and iron. These permanent magnets have much greater strength than ordinary steel magnets. The permanent magnets are attached to the starting motor housing. These starters usually have more permanent magnets compared to the number of field coils in a conventional starter because no space is required for the windings. A permanent magnet motor operates in the same way as a conventional starting motor. Many starting motors have a solenoid that completes the electric circuit between the battery and starting motor. The solenoid also pulls the starter drive into mesh with the flywheel ringer. The solenoid is an electromechanical device that moves the starter drive into mesh with the flywheel ringer and opens and closes the electrical circuit between the battery and the starting motor. The solenoid contains heavy pull-in coil connected from the solenoid terminal to the main starting motor terminal. The final hold-in coil is connected from the solenoid terminal to ground on the solenoid case. The solenoid terminal is connected to the start terminal on the ignition switch. When the ignition switch is turned to the start position, current flows from the switch to the terminal on the starter solenoid. From this terminal, the current flows through a heavy pull winding to the main starting motor terminal. This current flows through the series field coils and the armature winding to ground, but there is not enough current to cause armature rotation. A small amount of current also flows through the hold-in winding to ground on the solenoid case. The combined magnetic fields of the two solenoid windings attracts the solenoid plunger and move this plunger ahead. Forward plunger movement pulls the starter drive into mesh with the flywheel ringer, and further plunger movement pushes the solenoid disc against the two large solenoid terminals. When this contact is completed, a very high current flows from the battery positive terminal through the battery cable and solenoid disc and terminals into the starting motor. Under this condition, the starting motor begins cranking the engine. Once the solenoid plunger is pulled forward, current no longer flows through the pull-in winding because equal voltage is supplied through the solenoid disc to the other end of the pull-in winding. Under this condition, the hold-in coil magnetic field is strong enough to hold the plunger in the engaged position. When the engine starts, the driver releases the ignition switch to the on position. Since current no longer flows through the ignition switch to the solenoid terminal, there is no magnetic field around the hold-in coil. The plunger return spring pushes the disc away from the solenoid terminals and current flow to the starting motor is stopped. The plunger return spring pulls the drive out of mesh with the flywheel ring gear and returns the plunger to its disengaged position. Some starting motor systems start a relay that completes the electrical circuit between the battery and the starting motor. Many of these motors have a movable pull shoe that pulls the starter drive into mesh. The flywheel ring gear. The magnetic switch contains a high resistance winding. When the ignition switch is turned to the start position, current flows through the ignition switch to the starter relay terminal. Current then flows from this terminal through the magnetic switch winding and the neutral safety switch to ground. This current flow creates a magnetic field around the starter relay winding, which attracts the relay plunger. Plunger movement forces the disc against the relay terminals connected to the positive battery cable and the starting motor. A very high current flow through the magnetic switch disc to the starting motor. The overriding clutch is the most common type of starter drive. The starter drive housing is mounted on armature shaft splines. The starter drive connects and disconnects the armature shaft and the flywheel ring gear. The starter drive housing contains four spring-loaded rollers in tapered grooves. The drive gear has a machined shoulder on the rear part of the gear. This machined shoulder is in the center of the rollers. When the drive is engaged with the flywheel ring gear and the armature begins to rotate, the rollers are turned so they move to the narrow end of the tapered grooves. Under this condition, rollers are jammed between the tapered grooves and the machined shoulder on the gear to the drive housing, and the gear must rotate as a unit. Therefore, the armature shaft rotates the solenoid housing and gear to the crank to crank the engine. When the engine starts, the flywheel ring gear momentarily rotates the drive gear faster than the drive housing. This action rotates the rollers so they move into wide end of the tapered grooves. Under this condition, the drive gear freewheels so it does not turn the armature at high speed and damage the armature. That's it for today. Thank you for watching.